So, ladies and gentlemen, the model that we saw yesterday during the final minutes of the session had introduced a key element of dynamic modeling, namely the dynamics, the behavior over time. And what we're going to be looking at now is an equally important element of dynamic modeling. It's introducing an environment in which agents are embedded and allowing agent-to-agent interaction through that environment. So two agents can interact with each other, okay? I've just called up AnyLogic. If this screen shows, remember that you can just minimize it here. It will always be here if you want to get it back. But we're going to go through an exercise where we build up a model to build on those basics that we saw yesterday. But we're going to introduce some new features in the form of networks, in the form of agents communicating with each other. In this case, communicating pathogen, but in other cases, it could just as well be communicating norms, attitudes, beliefs, etc. So, if you have a model from yesterday, I'd like you to close it. You can do so by going to this File menu and choosing Close All, for example, or by right-clicking on an existing model and saying Close All. And I'd like you to now create a new model. So how do you create a model? Who can tell me? Where do I go? File, New Model. And we're going to say here SIRS. Model. For those who that's not meaningful, maybe I'll call it contagion. Okay, it'll be a model of contagion. Contagion is a more general concept. It can include transmission of pathogen, but also transmission again of attitudes, knowledge, beliefs, etc. We will set the time unit, the kind of meter stick or yardstick by which we measure time, to be days. 1 will mean 1 day. We're going to say new. Okay. Okay, now, here we go. So having created that model, you'll notice that over here we have the model hierarchy. We have the palette, which we can use to add things into the model. We have our canvas with main being open. The reason I had you close the other models is we don't want to be dealing with many mains or many persons, for example. Okay, so suppose we want to add a person we want to add a person class to this population to represent personhood. How would we do that? Yeah, we do new agent type, and we're going to call it person with a capital P. Now, we could call it something different if we wanted. In some cases, we might call it patient. In other cases, we might call it citizen or worker or what have you. And in general, our models will have multiple types of agents. We might have a model which has inmates and corrections facility staff members. Or we might have a model with doctors and patients. We might have a model with a zoonotics type model where we have people and ticks, or people and service dogs, or what have you. So we're going to have person here. We're going to say finish, and we create a person class. Now, traditionally we've been using a little circle to represent things. I'm going to broaden our repertoire a bit. Let's go down from that, go down to the pictures area. Okay, there's a pictures area in the palette, which will give you a greater repertoire. If you really want to get fancy, you could do 3D pictures, but I'd ask that you stick to a regular picture for now. So from this palette and into persons, I'd like you to drag a person silhouette. I'd like to suggest the black one. And we're going to learn to manipulate that. Where did I go? Whither did I go? Well, in this palette, I chose the pictures area. When pictures came up, I chose a person and I dragged it in. I dragged it in to this crosshairs because, again, that will mean its logical position is the same as its visual position, okay? Now, having done that, we've done all that we need to do before adding an agent population. So how would we add, this is a theory of personhood. It's a theory of personness, what it means to be a person in this model. And we're going to add to it. But what's important is we give it the visual representation first for obscure reasons in any logic. How do we add a population of people? How do we have multiple people? Anyone tell me? Yeah, we go to main, and what do? We go to main, and what do we do for main? Make sure main is shown here on the canvas. What do? We drag from person over to main. That's right. And we're going to say here, this is population. And is that a population? If I just call it population, is it truly a population? No, we have to say it's a population of agents. Now, it's going to say, okay, by default there's 100, but hopefully from yesterday, we can be a bit more savvy. What can we do to allow this model to use different numbers of agents for different scenarios? We can add a what? Begins with a P. It's a parameter. We want to parameterize the model by the number of agents. In other words, same model, different scenarios would tell it to have different number of agents. So we're going to drag in from the agent palette a parameter, just like that. Okay? And this is going to be called population size. Okay? You notice I've spelled this in what's called camel case. It kind of goes up and down like a camel's back. And that's a popular way of writing multiple names together within one word. AnyLogic is very finicky. It's not going to allow you to make it two separate words. It's going to exhibit computational distress of a most unpleasant sort. And so you don't want to invite that. So put in one name. You can also put underbars. That's another common one. And there's different traditions that use these different things. I tend to use camel case. Ladies and gentlemen, what type is this? Is this a double? Is it a sex? Is it a time? What is this? It's an integer. It's a count. Ladies and gentlemen, it's a count. And we'll make its default value 100. If no one specifies something, we'll use 100. Okay, so this is called population size. Tell me, if we were to run this model and we were to specify a simulation that specified a population size of 1,000, would the population size be 1,000? What is missing? So we said population size. That's an aspirational thing. We added this. We made it an int. We made it 100. Great. What have we not yet done that we need to do? What have we not yet done? Where is the actual this says population size, but where is the actual population size operationalized? Where is it set, in fact? It's in the population. It says 100 there. It's still hard-coded. It's hardwired. It's exogenously specified as 100 right now. I'm going to specify it right now as this population size. My population size. Mine being main. If I put this and it's inside main, it's referring to main. If By the way, that should help understand why we use self when we're in main, setting the characteristics of an agent. If I have this and it appears in person, it's referring to myself as a person. This the population size. Great. Okay, ladies and gentlemen, the final thing we're going to do is we're going to set these things to appear at random places all over the space. Where do we do that? Anyone remember? Yeah, initial location. Man, you folks are good. Random location from 0 to 500. Now, I'm actually doing something bad there. And within these boot camps, I have civil wars in my head between the pedagogical side and my disciplinary side, or between when to introduce something. I said 0 to 500. The fact is that 500 is not privileged. I could change things so it should be 1,000. The window is 1,000 wide and would still be stuck at 500. I've hard-coded this. So what I'm actually going to say is draw a value between 0 and this dot space width. Okay, now that's a kind of a confusing looking statement. Let me go put it up on the big screen. Okay, here we go. Okay, so what's going on? Well, first I determine the space width. Maybe that returns 500. And then I draw a value between 0 and 500. Or maybe space width returns 750. And then I draw a uniform value between 0 and 750. This gets evaluated first, so it turns into a value. It's a number. And then this outer thing gets evaluated, turns into a number. It draws a number between 0 and whatever this was. So this is just calling it, it doesn't need any information to do its job, space width. It's just calling it without any, as we call them, arguments. And basically it's saying, hey, space width, give me back your number. We still do what's called call it. We still say, hey, give me your number. Give me your result. And we're just not giving it any information. It doesn't need any information to do its job. So that's why we have this begin paren, end paren. Okay? And this next one down, we'll say 0 to space height. Okay? Space height. This one. So the next one down for y is this. So this was for x, and this was for y. Why are we doing that? Well, maybe I want to change the size of the window. Maybe I'll show you how to do that. And I want it to automatically resize nicely. If I'm going to run it with a big window, I want it to use that big window. Okay. Okay, ladies and gentlemen, if you have that, let's run it now. Shall we not? Okay. Let's run this thing. And there we go. What do we see there? What are each of these black spots? Yeah, those are agents. Agents spread over the space. Now, that's nice. If we wanted to change the size of this space, we went up to main, for example, you'll notice that if you go to main and you scroll down in the properties, there's something that says width and height. Do you see that? And you can actually change that. But let's not do that yet. I'll come back to that. Let's not do it yet. Okay, who needs TA help? The TA stand ready. Sector 2, front, row 1. Okay. Okay. Who else needs help? Okay. Any questions on that? Okay. All we did was we showed this nice image. Okay. Now we're going to take this, ladies and gentlemen, in a different direction, okay? First of all, we're going to go to the simulation. We're going to have this run. The baseline will be 250. Do you see that? 250. Suppose we wanted to create an alternative scenario where we had really crowded, let's say 10,000. How do we do that? Anyone? Or let's say 1,000. How do we do that? Suppose we wanted to do a scenario where we had a population size of 1,000. How would we do that? Where do we put that? How do we create another scenario which has an alternative population size? This population size is 250. How do we do it? I heard. Yeah, we do new. We could do new, or we could copy that one. I mean, that wouldn't be a terrible thing in this case, but it's not necessary. So I'll say it doesn't really confer much advantage. Or I could just say population 1,000, or you could say pop 1,000. So that sounds noisy. Okay, population size 1,000. Boom. If we were to run that, what will we see? We'll see just denser, right? There they are. You can see clusters forming just by the statistics of it, the luck of the draw. Okay. Ladies and gentlemen, so we have this little model. Now let's start doing something different. So we're going to go and we're going to go to person and we're going to add a state chart. And the state chart is going to bring people betweenst three states: susceptible, infected, and recovered. Okay? So I'm going to have a state chart entry point here. And this is going to be called infection state chart. What did I do? How did I add that? Ladies and gentlemen, I went down here to agent and I dragged state chart entry point up to this, okay? And that puts a marker here that is going to be the point of entry for the state chart. Who needs TA help? Next, I'm going to drag in a state called susceptible. I'm going to drag in another state called infective. I'm going to drag in another state called recovered. Yeah, recovered. You notice when you put names of states, it shows them by default. With names of transitions, you actually have to say show name. Okay. I spaced those out unartfully. Okay. Ladies and gentlemen. Great. Let's now put transitions betweenst them. Okay? We're going to have a transition from susceptible to infected, and that will be called infection. Yeah. And then we will go and place a transition from infective to recovered. And we're going to call the one from infected to recovered, we're going to call that recovery. Okay? We're not going to have an exposed state for now. This transition will do show name. Make sure you press this show name to have it show the name. Once you have the name, it's underlined, you can drag it. Okay? Great. Here's our little state chart. Terrific. Okay, well, we're going to do a few more things here. So, just building on yesterday's learning, how would we have them change color? If we wanted to visually see which ones are, say, in each of these states, how would we do that? Anyone? What did we have yesterday, according to the refined traditions of the Queen's English? What did we have? We had a variable. Remember that? It was called color. Okay? And what was the type of that variable? It was other, but it was color with a capital C. And its initial value will make black. Okay? Are we okay with that? Okay. This is leading up to a Shakespearean joke, if you can catch it. Okay. So, ladies and gentlemen, now what I'd like you to do, we're going to change the color of this little guy. Now, what's confusing is yesterday we actually had the choice of color when we clicked on that circle. We could actually change color directly. There's no option here, and there's a reason for that. This is actually highlighting the group. Within this, there's a shape, but it's not manifested. So let me teach you a trick. The trick for this, as well as some other cases, if you go to person, the hierarchical view, and you expand person here, okay? And you go to presentation, and you expand person once more, there's a thing called shape body, okay? Sounds like it could be an ad for a new fitness center or something, but shape body, if you click on it, if you expand this here, shape body allows you to set the color, okay? I'm going to set the line color here, but I don't want to set it to a fixed color. I want to set it according to color. How do I do that? I have to do, what do I have to do here? Yeah. I will refer to the variable, but what do I have to do? I can't type the variable name here. What do I have to do? Yeah, you have to do this. Hey, okay, yeah, I already chose. Hey, come on, get back there, yeah. Okay, and so I'll say, what do I say here? Yeah, this dot color. There we go. I'm referring to my color variable. This is I'm referring to myself as a person. Hey, get my color variable. Okay, so that's great. If we were to run this, what would we see? Would we see anything different? No, it's still the same thing. So, ladies and gentlemen, how would we do it so that their color changes for each step of the way? Suppose we wanted this color to change. Do you remember how we did that yesterday? Well, each of these states, if you click on it, it has an entry action. Thank you. So I would say this dot color equals, not double equals would test, is it equal? This is actually making it equal. Color equals green. Okay, semicolon. This one, this dot color equals red. The final one, this dot color equals magenta. I'm putting a semicolon because I'm telling it to do something. It's a command. I'm saying, do this. And if it's just a value, if I'm like drawing a value between 0 and 500, I don't need a semicolon. It's just getting a value. Here, it's actually saying, do this thing. It's setting it equal. So I need the semicolon. It's what's called a statement in Java. Okay, so ladies and gentlemen, let's run this. And you'll see the effect we've so wrought. You see that? Out, black spot. See that? There's no black to be seen. But they're all changing together. Why are they changing together? It's a fixed timeout. It's a fixed timeout here, ladies and gentlemen. But we can do better, and we're moving towards better. Okay. Ladies and gentlemen, the first thing we're going to do is we're going to have a mean time to recovery. So in main, I'm going to add a parameter that's going to be the mean time to recovery. We're going to be able to have different scenarios which alter our assumptions about how long it takes to recover. I'm going to call it mean recovery. Maybe I'll call it mean duration of infection. Mean duration of infection. How's that? Okay. Alternatively, another good name would be infection duration in days, but I'll call it that. And I'm going to set its default value, ladies and gentlemen, to be 10.0. What does 10.0 mean? Days. Now, if I really wanted to be picky about it, I could actually choose its type to be a time and say it's in days and make it 10 days. That kind of makes it self-documenting. So that's not a bad thing. I won't dwell on that, but if you'd like, you can make its time be in days and say it's day 10.0. Maybe one of the TAs could investigate whether AnyLogic has improved its support for handling of these things, like auto conversion of times and so on.
Okay, so if we change it to hours, then it doesn't automatically make it hours, just as we put the hours up there?
No. Which is so close yet so far to greatness. Cheryl, I share your sentiments and vocalizations. Yeah, no, it's distressing. So close. Come on. Yeah, this is one of the reasons I feel ambiguous about whether I should teach that, because you'd expect it to be basically intelligent. So if you use something that happened to be measured in days, but you used it, in a context where it required to be converted to years, it would auto-convert it. But alas, not yet.
So does that mean that when you choose your initial, when you create a model, that you can't change your time?
You actually,
You could with fractions.
you can. Yeah. You could just be consistent about it. It's just that I would have hoped that if you could tell it this is measured in days, this other thing is measured in years, that when it uses them, it would be intelligent about converting them in the appropriate way. It's just, it's not. It has the information, but it doesn't act on it. The spirit is willing, but the flesh is weak.
So if you actually wanted this in hours, then would you have to then in the default value create a fraction then, like for 1 hour?
If you did it as hours, where if you could use it in, I'll show you, okay? We'll see how this is used in just a minute. I'm saying it's in days. Now notice I put this in main. Again, one of the most common mistakes is you put it in the wrong place. I put this in main, right? Why in main? So if I put a perimeter in main, why is that especially nice? Because I can change it across what?
All agents?
I can, actually, if it's in main, yeah, it will affect all agents. So that much is true. It can be a shared value between all agents. But I can change it between different what?
Experiments?
Yeah, experiments, scenarios. One experiment can make a could assume a large duration. Another one could assume a small one. It allows the experiments, without modifying the model, without going and futzing with the model logic, I could say, let's run this model with this assumption. Let's run it with that one. And I don't have to go in and futz with the model and forget to change it when I get a phone call in the middle of it. I forget to change it back, and then I discover it after I've submitted the paper that my assumption was wrong. Yeah, I've been around that. Been there, done that, for that sort of thing. Okay, so ladies and gentlemen, let's go to person now, and we're going to go to recovery. Ladies and gentlemen, we're going to go to recovery, okay? And we're going to set this, not from being a timeout, but a rate. It's going to be a chance per unit time of recovering, okay? And it turns out, some of you may know from the properties of the exponential distribution, or may know from theory of stochastic processes that if you have something that's exponentially distributed, the mean time is 1 over the rate associated with the exponential. So this rate, take it from an old man, this rate is 1.0 divided by the mean time, divided by this, and it was called mean duration of infection. Now, I'm going to do something that's deliberately wrong, show you the stress, and then we're going to correct it. Mean duration of infection. So I'm going to say this. So what I'm saying is, if let's suppose I'm on average, I have prediabetes for 10 years before proceeding on. The rate associated with proceeding onwards is 1 divided by 10, meaning about 10% of those people leave each year, which kind of stands to reason, right? If let's suppose it were just 2 years, then about half those people would leave each year. Half the first year, half the second year. So the rate is 1 over the mean time. If the mean time is really long, 100 years, then about 1% of the people leave each year. If the mean duration is 2 years, about half. 10 years, about 10%, so 1 over 10. So if we have a rate transition, this is just a standard exponentially distributed residence time. You're in there for an average of mean duration of infection. The rate associated with it is 1 divided by that. What that means is they'll be in it for a mean time of whatever this is. However, if we put that in and we try to build, it'll be terribly unhappy. It'll say, I cannot find it. Why? Why can't it find it? Where is it?
That's in Maine.
It's in Maine. It doesn't know it's in Maine. It's somewhere else in the model. So we have to say, just like we say this to mean it's inside me, we say Maine dot mean duration of infection. And now we're cooking with gas. Now I do builds and it's a happy camper. Yes.
Drag to the left a bit.
Drag
Yeah,
drag this.
this way, the other way.
Oh,
Yeah,
this way,
okay.
okay.
They were just asking, you see the per day like there for the rate?
Oh, yeah.
You can-
Okay, yes. So this is where distress, computational distress besets me. And where I think any logic has fallen short grievously and needlessly, gratuitously, grievously. So, Cheryl, wouldn't it be nice if you said this is a per day rate, if it would automatically convert it, to the appropriate unit? But it doesn't do that. So this is a per day rate. So again, it'll be like 10% leave per day, or 1% per day, or if mean duration of infection were 2 days, half per day, 0.5 per day. Okay, so that's what that is, ladies and gentlemen. That is what that is. Okay, so if we were to run this now, what would we see? What would we see? Would they all change in succession? Well, they do change to their first one. But look at this. What's going on now? What's going on now? What's happening? Well, some of them have become recovered, and some are still, what? Well, now they're all recovered. Okay, because they recover at different times. The mean time, the average time, is whatever we specify. In this case, it's 10, mean duration of infection, specified by this scenario. Or here, it would be 10. But they change at different rates. Some go earlier, some go later. It's stochastic. Some earlier, some later, like the Waidarian model shown yesterday. Okay, so any question about that? But we're setting our goals for something higher than this. This is just rehearsal of what we've been doing. It's repackaging it in a slightly different way, in a way with person shapes. But now, ladies and gentlemen, something is going to happen that you have not previously seen. Okay, so this infection transition, I would like you to click on it. Right now, it is set to be a timeout. After one time unit, 1 day, everyone transitions to infective. We're going to change that now to be what's called a message transition. What that means is it's not going to be triggered by any internal logic to this person, typically. Well, not to this state chart. It'll be on receipt of a message. It'll say, hey, make that transition. And guess who's going to send the message for most cases? Another agent. An agent who is infected. So this is going to be a contact process. It's going to be this agent infects this other agent. And just like I might transmit pathogen, here I transmit a message in lieu of that pathogen. Now I can make that message pretty fancy. I could keep information in it. I could say what strain of infection it is. I could say what rumor I'm passing or whatever. In this case, I'm just going to gloss over that, okay? But we could have models that will do that. Ladies and gentlemen, I would like now to run this model. And I'd like you to anticipate what's going to happen. I'm going to run this model. I'm going to run it. What's going to happen? What do you think will happen? Will we see some neat stuff? I could run it and run it and run it.
Until you receive a message.
Yeah. So why isn't anyone getting infected? Because there's no one to infect them. We could run this till the cows come home. And there's no message that's going to be received. So what do we need to do? We need to send a initial message, ladies and gentlemen. There's actually several ways we could do this. But there's another thing too. Because, ladies and gentlemen, we need to have a way the message can transmit from one to another. So I'd like you to watch this. This is going to be a key step, and it's a step that's easily missed. So I'd like you to mark my words. Do you see up here in person? I'm viewing person here. Do you see in person there's a thing called connections? I'd like you to click on connections. Okay? And I'm going to say draw line connecting agents. Okay? Now, by itself, this is not going to do anything. This is just going to make any connections that are imposed elsewhere visible. So if we were to run this, we'd still see no difference. This is just basically getting it ready to display connections here. Boom. If I ran it, I don't see anything different. But we have to do one final thing, ladies and gentlemen. Ladies and gentlemen, one final thing, okay? Here. We're going to go over to main, and we are going to select main over here. Select main, and we'll drag down, and we're going to set a network type to be a random network. This is also called excuse me, what am I doing? A distance-based network, not a random network. And the connection range will be 250, okay? 250 units of space. Now, it turns out in AnyLogic, units of space are also have distance associated with them. Yeah.
Where did you do that?
Okay, so I went to main. This is great. I welcome those questions, like where did I do that? So go to main, scroll down, so select it, view it in the properties, and I scroll down to an area we haven't looked at before called space in networks. And there's a thing called network type. And I selected distance-based, and I made it 250. Okay, can we run it now? Can we try running it? Let's run it. What do you see? Okay, or if we run the one with size population 1,000, it's even denser. Boom. It's building it. Boom. Okay, it's very, very dense, ladies and gentlemen. Okay.
Can I just see the,
Yeah.
on your infection transition?
You got it. You got it. Infection. All I did is I changed it to be message. Get the line. Oh, yeah, thank you. So I went to, so this is in person. I went to connections, and I scrolled down to the bottom, and there's under animation, there's a thing that says draw a line between agents, okay? Okay. Okay, ladies and gentlemen, we've seen a very dense network. I'm going to scale that back. I'm going to go back to main, scroll down to where it says connection range, and I'm going to change it to 75, okay? 75 units of distance. So what did I do there? I went to main. I went up here to the properties, and I scrolled down to where it said connection range. This is just before network type. I went to set it to 75 connection range. Okay? So in main, selecting main, in the properties, scroll down to this area, space and network, and I set connection range to be 75. Okay? And now if I go run it, you should see something like that. Do you see that? Oh? Now we have people. They're susceptible to infection. And they're embedded in a network that can transmit infection. We just need one final thing. What is that thing? It's a spark.
It's looking really dark.
Sorry?
Even I changed that connection range to 75, it's still looking really dark.
Okay, the connection range was changed in main to connection. So Ashish needs help up here? No. Okay. You got him. Who needs help? Who needs help? Megan, over on this side. Sector 1.
Which population number are you running at now?
250 for this one. For this one, it's 1,000. But for this one, it's 250. Oh, I'm sorry, this one, 250.
So your little example was 250.
Yeah,
Okay, so we close that.
this is 250.
And then just right on your simulation.
Okay, ladies and gentlemen, we can do this in two different ways. I'll show you two different ways to start the infection, okay? So, ladies and gentlemen, if you go to person and you click on the little icon in person up the upper left, I'm going to make it so when we click on it, we're going to send a message to this agent that's going to, okay, to infect them, okay? Okay, so here we go. We're going to send a message to the current agent, okay? I'm going to say this dot myself send, and I'm going to say it's sending it to myself, and the message is going to be infected exclamation point, and the destination will be myself, okay? So I'll put it up on the big screen. There it is. Oop, this should be infected. The actual message right now doesn't matter, okay? We'll later start to get more picky about what our message, but it's unconditional. No matter what the message is, they're going to get infected. Great. So we're going to, basically when you click on this agent, how did I get there? I clicked on this guy. In the properties window, I scrolled down to advanced. I had to expand advanced. I went to on click. So what this is a so-called handler. It says, hey, when this is clicked on, do this thing. So this is a command. I'm saying, that's why this is semicolon, saying do this. And it's saying, hey, send myself a message that says infected. When I'm clicked on, send a message that says infected to myself. Okay. So if we do this, and we run this, and we were to click on a person here, what's going on? If we click on people, what do we see happening? They get infected, but are they spreading the infection? Most certainly not. They're getting infected, they're proceeding to recover. We're afflicting them, but their afflictions are a personal matter. They do not spread them. So we have one final thing to do. What have we not done yet? Yes, Terry?
So, I guess the other thing for me, some of mine turned infected and some of them went straight to recovered also.
That's because they recovered very quickly. You just couldn't see it immediately.
Got it, okay.
Oh. Okay, who needs DA help? Do you see by clicking on people, do they change? Okay. Why isn't it spreading though? Well, we have people susceptible to infection, but other than us clicking on it, we don't have anyone spreading it. The infection is not spreading to anyone. So let's change that. Ladies and gentlemen, within the infective state, we're going to have them, as long as they're infected, we're going to have them periodically contact some of their contacts in the network. And infect them. Reach out, contact them, and infect them. So, through the palette, we're going to drag one final transition. But this transition is going to be a different type of transition. Ladies and gentlemen, we're going to have this transition go from infective back to itself. I'm going to drag it so it comes from itself, goes to itself. Here. It's going to be a contact transition. I'll call it contact. It's going to go with a rate of 1.0 per day, approximately 1 contact per day. And at that point of contact, I'm going to contact one of my random members of my contact network and send them a message. So I'm going to say this dot send to random connected, and I'm going to say infected. So let me put it up on the big screen. There we are. Oh, no, yeah. Again, it's a command. I put a semicolon. And for reasons I'll show you, the actual message here is somewhat immaterial. If you're going to use strings for messages, you have to be very careful about spelling them correctly, and they're not the best way to use messages. Better use an option list. And you'll say, send to random connected. I didn't type that. I auto-completed it. I don't know if you noticed that.
I did, and it doesn't auto-complete on mine, but
Oh.
I can ask Diego.
Yeah, if you do, maybe you have to type enough. Do you want to, Jason, check that out? Occasionally there's autocomplete flakiness in any logic. Okay, so what's going on? Every day on average, about 1.0 times per day, we're infecting a random neighbor. Who needs help? So what's going to happen now when I click? Anyone? What's happening? Ladies and gentlemen, what's happening? Ladies and gentlemen, so if I run this, will I see an immediate outbreak? Will I see an outbreak here? Is there an outbreak just by running it? What do I have to do to start an outbreak? Click. And once I do that, what starts to happen?
Sending messages to each other?
Yeah, messages mean contact. They contact each other. And if an infective contacts a non-infective, a susceptible rather, they will infect them and it will spread. And there we go. Yes, just by the luck of the draw, people didn't send him a message. They sent, because each time they're sending a message, it can happen because each time they're sending a message, they're sending it to a random one. Maybe the person they're sending it to this time is already infected, and they don't send it to that one who isn't. He's just a lucky person. Okay, ladies and gentlemen, you know, the magenta doesn't work so well visually. I'm going to change it to gray, G-R-A-Y, for recovered, just because I find magenta is hard to distinguish. So now we have a clearer contrast. Even that is not so great because it kind of blends in. Well, maybe stick it. Okay, so ladies and gentlemen, what happens now when the infection spreads? Can anyone tell me? So if I click on one, He's spreads, and the others will start to spread it. Why? What's going on? Let's walk through the reasoning. So I click on one of them. If I click on one of them, it's going to run this on click. It'll send that person an infective message. That person was in the susceptible state. Now they're coming to the infective state, right? Okay. Once in the infective state, what are they going to be doing? They're going to be, until they recover, which will occur in an average of 10 days, approximately once per day, they're going to send a message to a random person to whom they're connected, saying infected. Now, that person to whom they're connected might have been the one who infected them, or might be another one who's already infected them, in which case it won't make a difference. That message, there's no message transition from this state. So if someone's infected or recovered, they're not going to be affected by that message. But if that person to whom they send the message is susceptible, that person who receives the message will get what? Infected. They'll get infected. And they'll become infected. And then they'll start to send these messages to their contacts. And then it will spread. And some of those contacts who are susceptible will get the message, will get infected. And it will spread out. So we see this spreading right now. We see it spreading, and in many cases it spreads to the whole population before they recover.
Is there some bizarre little logical quirk that there's always one that doesn't get infected?
No, no.
Mine got infected.
Oh, it's because you're running it with this. Yeah, but it's because you're probably running it with the same random number generation. So if you were to go down in the simulation, remember that by default, any logic is running it with the same so-called fixed seed. If you set it to random seed, they're going to pick, it's actually the structure of the network will be different. They'll pick different neighbors so now you're going to see a somewhat different spread. Okay, good question, but yes.
Question about the logic within the state chart.
Yeah.
From an infection perspective, this makes complete sense that the people who, like you said, are already infected, it doesn't make a difference with the ones who are susceptible. But is it just because of the initial entry? Because I'm not seeing where the infected would specify if you're infected, it doesn't affect you. If you're susceptible, it does. I guess I'm not seeing that in the state chart, so I'm just trying to figure out
Okay.
where that line is to the susceptible people getting infected but not the infected people.
Mm-hmm. Good question. So this, if we think about trying to figure out how to best sort of address that question, because it's an interesting one. It's one I've pondered how to communicate before. So this transition is the only message transition currently in the model. It's the only transition that's triggered by a message. The fact that it's coming from a susceptible means that only susceptibles are subject to that message transition. So if they're, for example, in a recovered state and they get a message, they can't take this transition because they're not susceptible. The only way they can take it, it's contingent upon them being in a susceptible state. If they're in a susceptible state and a message arrives, they'll go down like that. But if they're in an infective state, they can't go down that message because it doesn't come from the infective state. If they're a recovered state, they can't go down that transition because it doesn't come from the recovered state. Does that make sense?
It does make sense, because I think just because of looking at the arrow, which then actually is not logical, I was interpreting that as the message comes from the susceptible people. It wouldn't, right? Like, so now I understand.
No,
It's dependent on it.
this is a transition from susceptible to infective. It's an action, part of whose rule for when it fires is you have to be in a susceptible state. Now, not only are the rules characterized by the type of transition, like a message transition or a timeout or a rate, they're further specific to the state from which they come, whence they come. So it's only if you're in a susceptible state that you're subject to infection. Does that make sense?
Yeah.
Okay, so ladies and gentlemen, I'd like to add a fateful transition. I'd like to add a transition back. We're going to alter. We've been, well, okay, let's do one thing before that. I would like to have a normal sized population. This one is called simulation. Let's call it baseline. This is kind of our reference simulation, okay? It's not privileged, but it's the one that we'll compare to. Often we have a baseline that kind of represents the status quo or the current situation, the default situation. This is going to be that, okay? 250, a mean duration of infection. Ladies and gentlemen, let's copy this and let's paste in another one that's just a variant on it. It's going to be called baseline 1 initially, but we'll call it long duration of infection. Very commonly, when we run experiments, we want to run them with only one thing different between them. So we can understand how does just changing one thing change model results. In this case, we're going to change duration of infection. I'm going to change the duration of infection here to be, I'm sorry, I said long. Let's make it short, okay? Say duration of infection 5. I'm going to make it 5.0. 5.0. How do you think that will affect things? How might that affect the result? Anyone? Well, let's run it. It's not clear. We have trouble thinking these things through in our head. This is a theory, and it's not clear what it will do. Okay, so now let's click on someone. And we can spin it up, and we could speed it up. Well, here on mine, I have a few people left over. More than a few. This one, this one, this one, this one. It's not immediately obvious just because the colors. And again, I stand to have a better color. What would be a better color than gray? Blue. How about blue? Okay, should we say? Let's try blue. Okay, there we go. Brings out great contrast. And you'll notice this one wasn't infected, this one wasn't infected, this one wasn't. Right? Let's try a duration of infection here of 2. Okay? So what did I do? I just copied this. I went up to here and pasted. Why am I doing that? Because then I don't have to change the population size to be the same as the baseline, etc. It's just, so I'll say duration of infection 2, and I'll change it to be 2.0. What do you think will happen now? Sorry? Okay, duration of infection 2. Oh, look at that. What happened? Can you see it from back there? What happened? If you do duration of infection 2, I'll even change it to, it's random number. I changed it to be random seed, so each time it's separate, it's distinct. If I click on someone here, how far does it go? It almost dies out. Why? Well, it's not propagating effectively enough, efficiently enough. Each person is infecting on average fewer than one infected before they recover, even in this entirely susceptible population. It's not spreading fast enough or efficiently enough.
So is this an example that when the duration was 5, the emergence was different than when it was 2?
Well, when it's 2, it's quite different from 5 and above, certainly. And it's probably somewhere like 4 and above or something like that. So they're qualitatively different. One, the infection really spreads, and this one, it basically dies out with a bit of petering out. But I want to change it a little bit further because I want to see another qualitative change. Thus far, what we've been changing our quantitative assumptions. Now we're going to change the structure of the model. Normally I would save a different version of the model. So I'm going to save this as version 1, and if anyone's having trouble, if anyone's struggling, I will post this post-haste and get it up there, okay? Give me a second here. And I will put this on the site for this boot camp. Here we go. So this is models built in class, and put as built, and I'll make this day 2. If anyone wants to grab this, we'll do this, but I'm just showing a version of the model because we've reached a sort of milestone, and then I'm going to take it in a slightly different direction, okay? So I'm going to go to models and contagion. Here we go. Boom. Okay, so it's up there. Contagion v1. Now, having saved away that version, I would do it in Git and other contexts. Now I'm going to draw a transition directly from recovered back to susceptible. And while I do this, I'm going to use a trick. If you double click on these transitions, you can get these little handles to drag them. Oh, hey, come on. Come on. There you go. Which can make them prettier. You can prettify the model. Okay? So here we are, a transition back. And we're going to have a mean duration of immunity, okay? And we're going to, sorry? Okay, there's trouble here? Oh, to turn, oh, okay. You have to double click on it. It'll turn into a handle, a little white handle. And once you have that white handle, you can drag it and bend it to your will. Now, if you double click it again, the handle will disappear. Double click the handle again, it'll disappear. Okay? Okay. Ladies and gentlemen, we're going to go to main. We're going to add a parameter, just like the other one. We had mean duration of infection. Now we're going to add a parameter, mean duration of immunity. Let me tell you a trick. Take it from an old man. If you, ladies and gentlemen, if you go and right-click, you actually click on a parameter or click on any other element, and you drag while holding down the control key. This is a PC trick. I don't know what its Mac equivalent is. You drag it while holding down the command key. It will copy it. And that's a nice thing, because sometimes we want to keep a very similar name. So all I did is I clicked on this, and while I'm holding down the click, I have the control key, and then I let up for the click, and basically it's duplicated it. Yeah, it's sweet. And I'll make this mean duration of immunity. And it's going to be a duration of 30 days. 30. Okay. Next, we are going to have go back to person, and I'm going to set this transition that goes back from recovered to susceptible to be what? Anyone want to guess? This is the mean duration of infection. Now, how do we refer to that? if we just type mean duration of infection, is that going to be able to be happy? What do we need to do? It can't find it. Why can't it find it? Because it's in, oh, sorry, mean duration of immunity. Why can't it find it? It's in Maine. It's in Maine. So I'll refer to Maine.mean duration. Oh, okay. It's exhibiting. Okay. Sorry. This is my model's exhibiting distress. Okay. It's giving spurious error messages here. Okay. Maybe because I was futzing with that thing. So there's two ways to deal with it. I know this problem. And I'm going to close the model and I'm going to reopen it. Boom. And I'm going to reopen it here. And now I'm going to build it again, and it's going to be a happy camper. So sometimes AnyLogic gets in an ornery mood, and it starts to generate a spurious error message about not finding a transition. And the secret is close the model and open it again. Okay. So the duration associated with this timeout transition is mean duration of immunity. How do you think changing the structure, so we've changed the structure of the model. We haven't merely changed parameter values. We've changed the structure of the model. How do you think the presence of this transition is going to change things? Anyone? Anyone want to hazard a guess? Let's run the baseline. I'm going to click on someone. It's spreading. What's going on now? Is the infection going up, coming down, and we have no leftovers, or we have 2 leftovers, or we have 5? Is that what's happening?
Some kind of stabilization.
Well, it is a sort of stochastic equilibrium where it's oscillating around. So what you'll see is continued oscillations. Now, this is a little bit ad hoc, looking at it visually. Visually is very powerful to match certain patterns, but sometimes we want to go beyond that. So in the closing minutes here, I'm going to teach you another few tricks. If you go to Maine, let's go have a count of the number of people are susceptible and infected. Shall we not? Let's just do a number of infectives. Be easy enough. So I'd like you to go click on the population. What do we need to add to the population to compute, to have it capture the number of infected people? Anyone? Yeah, we want to add statistics, ladies and gentlemen. Statistics and statistics live in the population. So we go to the population, we're going to say a statistic, and it's going to be, we'll call it count infectious, okay? You could call it prevalent case count. That wouldn't be a bad idea. But maybe we'll call it count infectious here. Okay, so I'm going to say it's a count. And what is it counting? Well, remember, we refer to each person in the population. The first person, they call them item. Remember that? And we say, hey, item, is this thing true about you? And then we go to the next person and call them item. We say, hey, item, is this true about you? So we have to give the rule we're going to apply to each of those people. Item dot, and we're going to ask in state, are they in the state? Oops. In state And the state is going to be person dot infective. Okay, it's infective with respect to person. Maybe we have a model with not just persons, but with mule deer in it. Or maybe it's a model with dogs. Or maybe it's a model with armadillos that carry pathogen. And so there might be infective with respect to different things. This is infective with respect to person. It's an infective state in person. So we have to say person.infective. So let me go put that up. I said count infectious. I said count. We're counting the number for whom this is true. Okay? Boom. And I'll put it on the big screen. Boom. There we go. Item is the name of the person. It's sort of it's the designation of the person. It's calling whoever it's examining to see if this criteria is true. This question is true. It's calling item, and it's asking, are they in the state? And this is the name of the state. It's infective within the person. Okay. Okay. Let's run it. Are you okay with that? Can we run it? Who needs TA help? Iden stands stalwart. Okay, let's run it. Let's run it. And if we go and we kind of start up an infection, come on. And here we go, look, we'll actually see over time a count of the number of infectious, and you'll see it oscillating here. But it's a little bit less than optimal in terms of how it presents that information to us. Flashing numbers are not great for conveying these things. So now I'd like to take it one step further. Ladies and gentlemen, I'd like to introduce you to something that will be more apparent from Winchell's case study presentation, and perhaps from Wade's as well. Namely, AnyLogic has some pretty nice visualization capabilities for displaying data. So I'd like you to go to the palette. I'd like you to go to the analysis area of the palette. And I'd like you to drag in a time plot into main. Make sure you drag it into main, ladies and gentlemen, not into each person. Each person can have a plot, but that won't be all that effective in this case. So I'd like you to drag it in to main. So, so it's this guy here. It looks like a little histogram with a cumulative histogram superimposed on it. It's just under space markup. It's about 3 down from agent. And we're going to call this population state time plot. So it's kind of the states people are in, okay? Wade, when you show your chickenpox model, you have outputs.
Yes.
Yeah. In the data area, we're going to add something, and this will be count infectives. The title will be count infectives, and the value here will be the value of that statistic. Where does that statistic live? So what did I do? I went to this analysis. I added a time plot into main. I went to the time plot, I called it population state time plot. I added, using this little button here under data, a thing called count, and I called it, the title is count infectives. It's a value I'm displaying, and the value is going to be the value of the statistic. Where does the statistic live? Where do we define the statistic? Begins with a P, population. So I say this dot population, my population dot count, and then autocomplete, count infectious. Probably should have called it count infectives. Okay. Ladies and gentlemen, we've just added something to count the number of infectives. So, I'd like you to run this model now, or build it, make sure it's okay. The TA stand ready. Narges and Iden are both waiting for questions to arise. Whoa. Okay. Okay, let's run this now, the baseline. Who else needs TA help? TAs are here to help. There we go. Now let's scroll up. What do we see? Rising in the firmament. Control space will be your friend. Autocomplete helps prevent these things. So now we see a graph. Now we could quibble with it, like maybe we want to set it to be a longer time frame. But you can see the oscillations. What is this showing? A graph of what? A graph of the count of infectious people. How did it know to compute the count of infectious people? Because it's using the what? Statistic that we defined. Now, we can go and we can engage in frobbing behavior on the graph. Is that not right, Christine?
It probably is, yeah.
Yeah. And so I think I'll do that. So ladies and gentlemen, I suggest that you select the graph, and we're going to frob just a few things. So in the scale area, we'll set it, instead of displaying a time window of 100, we'll set it to 1,000. And just above that, for this chart as well, if you select the chart, go down to scale, we'll set it to 1,000 for time window, and we'll display up to 1,000 latest samples. That will give us a longer window. So how did I do that? I went to Main, I went down Main, as they say in New England, and I click on the chart, I scroll down to data update, and I change display up to so many latest samples to be 1,000, and I set the scale, the time window, to be 1,000. So following that chart frobbing, you can run the baseline again, and now you can infect a person at your leisure, and this will display the chart. Okay? It's showing a somewhat broader swath of time now. What's notable is the fluctuations. An aggregate model would show this is going to an equilibrium, a fixed equilibrium. Here what we see is the persistence of oscillations over a longer time period. As individuals get infected, recover, lose immunity, and thereby are subject to yet another wave of infection. Sorry? Yeah. So this one is already labeled. It says count infectives. That's the actual graph. The axes here, it's a good question. I don't think there's an easy way, there's not a trivial way to do that built in, but what you could do if you want to label the axes is you go to Palette, you go to this presentation area, and what you can do is you could drag in text that you use to label. So for example, we could say, count infectious, and that will, that could be used as a label for this. I think, yes, you can even rotate them around and drag them into position. So there, and then we could label this other one as time. So this would be time. And we could change the font as we see fit. Maybe to 18 point or 20 point. Boom. And there we go. Hey, get back here. Hey, come on. There we go. 20. Okay. Okay, and we will run it now. And now we have labels that I've added in. I'll start off the infection, and there are some labels added in. Okay. Time and count infectious, and I could drag them into a nicer position if I want to prettify it. Okay. I could examine how does this change, say, for a duration of infection 5. If I only have 5 instead of 10 as the duration of infection, how does this differ in terms of the dynamics? Let's go see. What happened here? It died out, ladies and gentlemen. Let's try that again. Let's try running it. Hey, it died out. Let's try that. Boom. We could get brief peaks where there's a spread of infection that lasts a short time, but it's defined. That's quite a qualitative difference, actually, from that other one, where it just stayed endemic. But it depends some on the population size. This one lasted for a little bit longer by chance. So we can get these outbursts where it bursts up. We could also look at larger populations, all squished into the same place, the same space, right? Here we go. If we were to click on a person here, now we have a much larger population. And now it goes to something that's a little bit more tightly bounded in terms of a stochastic equilibrium around a certain point. So, ladies and gentlemen, we've seen how we can set up a model which demonstrates contagion. This model captures contagion because when people are infected, they send messages to others that can infect them. They have contacts with others in their networks. And when a person's susceptible, and specifically when they're susceptible, if they get a message, they get infected. And they proceed to the state of spreading infection. That infection spreads over networks. And the networks are set up in such a way that they connect multiple individuals. The infection spreads over the network. So when a person in an infective state sends a message, it goes to a random person to whom they're connected. And that person can then become infected if they're already in a susceptible state. We've seen, moreover, that we could define, like before, we could define statistics. But what's more notable is not only are these statistics visible, if we click on the population, but they're also visible in a graph. And we've set up a graph that can display those statistics. How did we do that? We set up this graph here to show a value along a certain, with a certain curve here. And this value was calculated via those statistics as determined by this population. We defined this statistic, count infectious, and then we used it in this graph in a fairly declarative way. We told it, hey, to display the count of infectives, determine that with this. And behind the scenes, there was it was updating the graph every one day, and it was displaying up to 1,000 samples. In other words, data for 1,000 days. And that allows us to capture this spread. But there's one thing here that's a little bit for the birds. We're sending a message by manually clicking. And that's all okay. I mean, it allows us a certain amount of flexibility. But suppose we wanted to instead of clicking on an agent to send a message, suppose we wanted to have it automatically infect an agent when the model starts. Let's show that, and then head to lunch. Yes. Okay. So, ladies and gentlemen, I'd like you to go to the palette one more time and go to agent palette. And I'd like you to drag into main, not person, but main, drag in an event. And this event will be called initial infection. And this is the first time we've used an event. But you can be most assured that it is not the last. An event describes one or more statically scheduled ahead of time, for most cases, planned occurrences. In this case, we're just going to have one. Later, we'll use it for reporting, where we use many. So this is going to occur once at time 0, and the action that we're going to have here is the following. So an event fires at one or more times. This is just occurring once. That's why it says. So an event that we dragged in, we can set it, does it occur once, or does it occur cyclically, or occur in a more flexible way based on user control? This is going to be occurring once. And the action that's triggered by this event will be as follows. Get ready to type in the action area. Okay? So the action will be this dot deliver to random agent inside. That's a bit of a mouthful. Make sure you use autocomplete. So it's this dot del, and then you can do control space. Deliver to random agent inside, and the message that you deliver will be this message, infect, exclamation point. Maybe it's infected. If you're using strings, you got to be very careful to use them consistently. But here we're just treating it, no matter what string that's received, we're going to get infected. Okay.
As it being lynched, can I ask why it's not sent to random? And I know there's a good reason, I just don't remember exactly what it is.
Why it's not sent to random?
Yeah, why it can't be sent to random?
Oh, yeah.
I know there's a good reason.
There's a good reason. So the operative word here. So we're putting this in an event. May I remind you, in main. Okay. So this event, we're putting it in this initial infection event in main. the operative word here is inside. We're sending it to an agent that's inside of Maine. It's one of the agents Maine keeps track of. If we did deliver to random, it would try to deliver it to other Maines. Or if it said to random connected, it would say, what is Maine connected to? Maine actually has connections. It would say, oh, there's no connections. Okay, no one to deliver it to, something like that. So here, because we're doing this in Maine, we have to deliver it to a random agent inside, okay? That's not a very, I don't like this, but I don't like other things in there as well, but I live with them, because it's the least bad. There it went. Christine, you saw the snuffleupagus. See or not?
So did First Smith, did he come in?
What's going on?
Maybe the machine decided to contact?
Yeah, I think, okay, well, this is a most curious thing. But we shouldn't let it get in the way of lunch. Okay, here we go. So the projector is rebooted. Okay, you can still see it up there. Yeah.
Do you have maybe one of those phantom keystrokers?
Okay, so ladies and gentlemen, I'm going to run this. An initial person is automatically infected as hoped, and it will run it as we see fit. Okay? I just closed my name logic, sorry. So it's working. It just runs it automatically and without a need for clicking. It'll just run it immediately. So in other words, it will infect that initial agent directly. Okay? Are there any questions on that? Questions on this exercise? Yes, Rifat.
So random.
Mhm.
So it will, can we say what will be the probability, or it will just decide by itself?
So that send to random agent inside, it's a good question because it is weighting all agents equally there, and it's just picking one with uniform probability. If we wanted to pick some with higher likelihood, like those who are more connected, for example, we would need more complex logic. Similarly, if you wanted to send to, say, 5 randomly selected agents, distinct agents, we would, there's a very sweet way to do it, but like Fermat, there's not time, or for him space, for me to describe it right now. But if there were interest after lunch, I could provide the requisite instruction. Okay? Okay. Other questions? So now we have, when we run this, an auto-infecting model. There's an initial message being sent by Maine itself to an initial person, and did that person recover automatically? Here we go. Did I lose that? No. And that will, in general, start off the infection here automatically without any need to click. Now, there's a third way, which I'm not showing you, but which we'll visit at a later time. We could start a certain fraction of the population infective, and then there's no need to infect someone directly. They actually start in an infectious state. And that would be readily accomplished. All we need to do is to, when they come into the state chart, some would go to susceptible, some to infective, and some to recovered. So that's readily done. Just like in a model, say, of chronic disease, we want some people to start without heart disease and some smaller set to start with heart disease, for example. Okay? Okay. Ladies and gentlemen, the faculty club beckons, a buffet of sumptuous proportions. And I'd invite you to partake of it. We will restart here at about 1:15 or so. Okay? Thank you very much. And look forward this afternoon to going through some guidelines for model conceptualization, as well as to extend aspects of our facility with AnyLogic, and to get started on project work. Thank you very much.
This